Hello everyone, I am Mert. Today I will present our work, Are labels needed for instance incremental learning? Instance incremental learning consists of sequentially learning object instances as they arrive by, such as phone1, phone2, cup1 or cup2. To achieve this, researchers utilize instance images as well as their fine-grained labels, and then they use it to expand the linear classifier per instance. Such an approach is inefficient because of two things. First, the size of the output layer grows linearly with the number of instances, so it is weight inefficient. Secondly, the learner always depends on fine-grained instance labels, which is limiting label efficiency of these techniques. To that end, in this paper, we ask ourselves, are labels really necessary for instance incremental learning? We present visual self-incremental instance learning, VINIL. VINIL trains an embedding network by extracting its own supervision signal directly from the data via self-supervision. Hence, VINIL is simultaneously weight and label efficient as it only learns a single embedding, no matter the size and the number of instances that the learner will observe through its lifetime. VINIL is trained via combining two main loss functions. The first loss function is a contrastive self-supervised learning loss to extract representations. To do this, we basically generate two different views of the same input instance via rotation, color jitter, and every other augmentations, and then try to match their embedding within the feature space. To combine extraction of self-supervised signal, we basically use regularization or replay to retain the learned representation. For regularization, we basically force the weights of the backbone to be similar or to change smoothly across different learning sessions. For replay, we basically store a subset of the previous learning tasks and then we replay them also via self-supervision during learning of new information. We experiment with two large-scale object instance datasets, namely Core 50 and iLab 20 million. And then to perform evaluation, we resort to nearest neighbors and report accuracy and forget rates using the nearest neighbor performance. We contrast our work to instance label supervised variants. With this work, so basically, we perform an evaluation of label supervised incremental learning versus self-supervised incremental learning. As a learning protocol, we receive a single object instance per learning task, such as phone 1 and phone 2, and continue learning. In our first experiments, we basically train and test on the same data set, and then our first observation is that VINIL is more accurate and less forgetful across majority of the settings when you consider the performance of accuracy and the forgetfulness. VINIL consistently leads to more accurate and less forgetful representations. Here, an important exception is replay. As you can see that label supervision outperforms same self-supervision within the same dataset when the labels are present. To better understand this phenomenon, we basically perform another analysis where we train and test on different datasets. Basically, we train on iLab 20 million and test on Core 50, vice versa. Firstly, we observe that replaying with labels lead to a strong drop in performance. As you can see, for example, replaying with labels leads to a 36% drop with respect to the original written dataset setting. This simply indicates that replay generalizes by overfitting, or in other words, replay overfits to the training source dataset. Secondly, no matter what dataset or setting or metric, VINIL consistently yields the lowest drop in accuracy, meaning that it can extract more generic features across datasets and tasks, which gives us promise, considering that Vinyl hasn't observed a single label throughout its incremental learning stages. To understand the merit of self-supervision, we conduct a set of analyses. Here, we report the performance across all tasks as they arrive by. In this figure, x-axis denotes the incremental learning time step, and y-axis denotes the accuracy per task. As you can see on the left, label supervised variant leads to a strong performance only for the current task, evident from the high performance within the diagonal. This simply indicates that label supervision biases the learner towards the recently observed task data, and it cannot retain its performance afterwards. In contrast, when you look at the performance of vinyl or self-supervision on the right, self-supervision can leverage the incremental stream of data to improve performance well across all tasks, hence leading to high forward transferability. As you can see, as the learner starts to observe more and more tasks, the performance across all tasks begin to improve, which gives us promise that to leverage a giant amount of unlabeled data on the internet. To understand better, in our second analysis, we focus on the activations of the penultimate layer of our backbone, which is a ResNet 18. Firstly, when we look at the label supervised variant, we observe that label supervision has a bias towards the background, so it tends to pick up on cues that are present in the context, which is not useful for instance incremental learning, and hence it basically fails to locate the target object of interest. However, self-supervision generalizes by directly activating on the target object instance, helping to explain the source of high performance. To better investigate this, we also perform a retrieval analysis. We basically take the features from the penultimate layer and we look at the nearest neighbor, 5 nearest neighbor, either with the label supervision or self-supervision via vinyl. And this phenomenon is more evident when we analyze the nearest neighbors here, as label supervised variant consistently retrieves different instances with the same background, which means the feature space is highly occupied or distracted by the contextual cues. However, as you can see here, self-supervision is able to retrieve the query object instance without being too much confused by the background, which means self-supervision can focus on the instance. To conclude, in this paper, we asked ourselves, are labels needed for instance incremental learning? Our answer to that is no. We propose vinyl that can continue to learn from incoming stream of object instances via self-supervision. Through extensive analysis, we show that self-supervision can extract more transferable features and can focus on instance level variation. Here, I would like to thank you so much for listening, and please feel free to ask anything. I will be very happy to reply.